Welcome to This Explainer. Today, we're tackling one of the absolute most frustrating bottlenecks in artificial intelligence, amnesia. Seriously, imagine learning a new language, but the very second you finally master French vocabulary, you completely forget how to speak Spanish. Well, that's exactly what happens to most modern AI models. It's a phenomenon known in the field as catastrophic forgetting. But what if we could fix that? Today, we're doing a deep dive into a really groundbreaking new framework called ARIA, which effectively allows AI models to continuously learn across a lifetime without ever overwriting their past memories. Okay, let's take a quick look at our roadmap for today. We'll be covering 1. AI's catastrophic forgetting problem, 2. Anchoring attributes with ARIA, 3. Filtering the noise, 4. Smart routing during inference, 5. The proof in the data, and finally, 6. The future of lifelong AI. All right, let's jump right into Section 1, AI's catastrophic forgetting problem, when learning erases memory. I really want you to think about this question for a second. What actually happens when an AI learns too much? For us humans, learning is cumulative, right? Every new concept just naturally builds on the last one. But for a neural network, the storage space, the actual weights and parameters, is strictly finite. When you force-feed an AI new information, it naturally has to adjust its internal weights to accommodate that new data. And in doing so, it frequently scrambles or just completely overwrites the representations it used to recognize older concepts. This brings us to a really important concept called Class Incremental Learning, or CIL. This is basically the holy grail of machine learning right now. The ultimate goal is to build an AI that can learn new classes sequentially over time without ever looking back at the old training data, and, crucially, without losing its accuracy on those old classes. Recently, researchers have tried using powerful vision language models like CLIP for this, matching images to text prompts. But surprisingly, even CLIP falls victim to catastrophic forgetting. So why does that happen? To really understand why, imagine our AI first learns to recognize a cat. It identifies all the key attributes, right? The fur texture, the whiskers, the pointy ears, maybe that general look of disdain. Fast forward, and the next task is for it to learn a car. Now the AI needs to learn totally new attributes like wheels and a metal chassis, but it only has data for the car right now, so it shifts its internal priorities. The researchers pinpoint 2 specific problems that occur here. First is extraction drift. This is where the AI literally forgets how to extract the features of a cat, shifting its focus so much that the very concept of a cat becomes distorted. Second is aggregation drift. The AI changes how it weighs information, suddenly deciding that metal and wheels are the absolute most important things in the universe, which effectively drowns out the importance of the fur and the whiskers. To solve this massive headache, researchers developed the ARIA framework. Let's get into Section 2, Anchoring Attributes with ARIA, the foundation of memory. ARIA completely overhauls the AI's pipeline by breaking down how it predicts things into 3 distinct steps. Step 1 is attribute extraction, which they call anchoring, locking down the defining features of a class so they never drift. Step 2 is attribute aggregation, or filtering, aggregating these features while aggressively stripping away useless background noise. And step 3 is inference routing, or matching, smartly routing a query to the exact correct stored memory. So let's break down step 1. How exactly do you lock a memory in place so it doesn't just drift away? Well, the ARIA framework uses a pretty clever mathematical method called Principal Geodesic Analysis, or PGA. Now, CLIP models actually map all their knowledge onto a multidimensional globe, which is known as a hypersphere. Standard, flat math doesn't work well on a curved globe. So PGA is used to calculate the dominant directions of a class, like the fur and whiskers of our cat, directly on the curve of this hypersphere. Once the AI learns a class, ARIA uses PGA to literally drop an anchor into the hypersphere. It effectively says, hey, this specific geometric coordinate is what makes a cat a cat. That anchor is frozen forever. Extraction drift, instantly eliminated. Let's see how this builds into the next step. Moving on to Section 3, filtering the noise, the aggregation phase. Okay, so once those anchors are set in stone, the AI has to learn how to weigh there for new tasks. ARIA uses lightweight task-specific experts. Think of them as tiny add-on modules to score these attributes. But we obviously don't want these experts learning bad habits, like relying on the blue color of the sky to identify an airplane. So ARIA applies a variational information bottleneck, or VIB. Think of VIB as a really strict teacher. It applies a predictive force, rewarding the AI for using features that truly matter. At the exact same time, it applies a compressive force, which actually forces the AI to throw away irrelevant view-sensitive background noise.
Finally, it uses an intervention constraint. It literally corrupts parts of the training image with noise blocks to ensure the AI isn't just relying on cheap visual shortcuts.
Now, this is where it gets really interesting. We can actually look at the optimization heat map for this VIB process on the CAIFR 100 dataset. We're looking at a grid that maps those two specific forces against each other. Lambda component on the vertical axis, which is the compression strength, and lambda int on the horizontal axis, which is the intervention constraint. The numbers you see inside the boxes, that's the final accuracy of the AI. Look closely at the colors. The lighter green and yellow areas represent lower accuracy, dipping down into the 87% range. But right there in the middle, you see this dark blue sweet spot. When the compression weight is set exactly to 1.0 and the intervention weight is set to 0.8, the accuracy peaks at nearly 89.24%. This perfectly proves that this delicate balancing act, forcing the AI to remember the core traits while aggressively filtering out the junk, yields the absolute highest performance.
To really visualize the real-world impact of everything we've just talked about, we can track a prediction stability analysis using a picture of a lock chamber from the Sun dataset. In the first scenario, the AI is trained only on its first task, and as you'd expect, it correctly identifies the image as a lock chamber with very high confidence. Now, the second scenario shows what happens after the AI learns a bunch of new tasks over time without the ARIA anchors. You can clearly see its confidence in lock chamber has completely plummeted, and the AI is actually confusing it with a canal. The memory has drifted. But look at the third scenario. Here, the ARIA anchors and VAB filtering are fully active. Across an entire lifetime of learning, lock chamber remains perfectly stable and top-ranked. The AI actually remembers. Which brings us to the final step in the pipeline. Section 4. Smart routing during inference. Asking the right expert. So, how does the AI retrieve this stored knowledge? ARIA solves this using optimal transport, or OT. Normally, models just use a simple point-to-point cosine similarity check. It's kind of like looking at a single label on the outside of a filing cabinet to decide if your document goes inside. But as tasks start to overlap, those labels get really confusing. Optimal transport is different. It's a distributional routing method. Instead of just looking at a single point, it calculates the mathematical cost of moving the new query to the entire distribution of a task's anchored attributes. Basically, it looks inside the whole filing cabinet before deciding. This ensures the query is routed to the exact right expert, avoiding misclassification even when the embedding space gets super crowded. But here's the crucial question. Optimal transport sounds mathematically intense, right? Does it slow the AI down? Well, when we evaluate inference latency and accuracy trade-offs, a really clear picture emerges. The bottom blue line on the latency graph represents ARU without optimal transport. The top black line represents ARU with it. Yes, latency does increase slightly, going from about 10 milliseconds to roughly 18 milliseconds. But contrast that with the accuracy mapped against latency. As the AI progresses through incremental learning stages, Task 2, Task 5, Task 10, the yellow bars, which represent ARU with optimal transport, stay remarkably high, ending way up in the 80% range. The red bars, which just use basic cosine routing, drop off drastically. So that tiny fraction of a millisecond added by optimal transport yields a massive multi-percentage point accuracy payoff. It is incredibly efficient. All right, we've seen the theory. Now let's look at the hard evidence. Section 5, the proof in the data, beating the state of the art. When evaluating ARIA's performance scaling, we can compare the CAIFAR dataset scaling up to 100 classes with the Sun dataset scaling up to a massive 300 classes. The horizontal axis here represents the number of classes the AI is learning sequentially, and the vertical axis is its retention accuracy. Look at that cluster of colored lines at the bottom of both charts. These are the previous state-of-the-art models like LTP, dual prompt, and RAF. As the number of classes increases, their accuracy quite literally falls off a cliff. Now, follow the top black line with the diamond markers across both datasets. That is ARIA. On CAIFR, it finishes a full 5.65% higher than the next best model. On the 300-class Sun dataset, it finishes 4.55% higher. While the older models steeply decline into catastrophic amnesia, ARIA remains incredibly resilient and structurally stable. Now, you might be wondering, is there just one specific trick doing all the heavy lifting here? Well, this ablation study on CAIFAR 100 confirms that nope, there is no magic bullet. The bottom teal line tracks the baseline model, which fails miserably. The blue line shows a massive jump just by adding the attribute anchors we talked about. The purple line maps the further boosts you get from adding that VibLoss filtering loss. And finally, the top black line represents the complete ARIA package, adding in the optimal transport routing. It's the synchronized combination of anchoring the attributes, filtering the noise, and smartly routing the data that creates this towering, industry-leading performance.
So, what does all of this mean for the big picture? Let's wrap up with Section 6, the future of lifelong AI, toward AGI. As the researchers brilliantly summarize, they have stabilized the learning process by anchoring extraction and refining aggregation, filtering out redundancy. In plain terms, ARIA fundamentally changes how an AI categorizes, stores, and accesses multimodal attributes. Instead of a chaotic, shifting web of data that just constantly overwrites itself, ARIA structures the AI's mind much more like a human memory system. It pins down core concepts while flexibly learning how to apply them in totally new, varied contexts. I really want to leave you with this final provocative thought today. The sheer inability to learn sequentially without forgetting has been one of the biggest roadblocks in all of machine learning. If frameworks like ARIA mean that AI can now learn continuously across a lifetime, accumulating knowledge task after task without ever losing its grip on the past, how close are we to true artificial general intelligence? Thank you so much for joining me on this deep dive into the fascinating mechanics of machine memory. I really hope this explainer gave you a clear picture of how we are finally solving catastrophic forgetting. Catch you next time.